Okay, without further ado, the Hardy-Weinberg equilibrium equations, which you're going to want to have on your cheat sheet. Hardy-Weinberg equilibrium states that P plus Q equals 1. These are the allele frequencies, where P is the frequency of the dominant allele, which is represented by a big letter, in this case A, and Q is the frequency of the recessive allele in the gene pool, in this case represented by a little a. Okay, those are the allele frequencies. And then the second part of the equation, these are the genotype frequencies. So P squared is the frequency of the homozygous dominant genotype. In this case, it'll be big A, big A. 2PQ is the frequency of the heterozygotes. Big A, little a equals 2PQ. And then Q squared is the frequency of the homozygous recessives, little a, in this example. If you take a look over here at the Punnett square, you can see where the genotype frequencies come from. So again, little p represents the dominant allele, so pretend like it's big A, and Q represents little a, the recessive allele. If we take those A's or P's across and down, and the Q's across and down, then P squared becomes big A, the frequency of the homozygous dominant. Q squared is little a, the frequency of the homozygous recessives. And then if you look, PQ and PQ, those are the heterozygotes, but there's two of them in this Punnett square. Hence, 2 times P times Q. Okay? Importantly, there's only two alleles, so P plus Q has to equal 1. And there's only 3 genotypes: homozygous dominant, heterozygotes, and homozygous recessives. The genotype frequencies also have to sum to 1. Okay, let's work through some problems and actually apply these equations. All right, let me walk you through one of these problems step by step. The series of steps that I'm about to do are exactly the same for all of these problems, whether we're talking about cats, whether we're talking about fruit flies, whether we're talking about humans' ability to taste PTC or sickle cell anemia. It doesn't matter. The steps and the math are all the same. Okay, so much to your dismay or perhaps delight, your neighbor has cats, a lot of cats. They have 100 cats to be exact, 84 of which are black and 16 are white. White is the recessive phenotype on this gene. So right out of the gates, the word problem is identifying the recessive phenotype. Okay, so that's really important. And then in yellow, I've highlighted what is the frequency of each genotype. So that is the question itself. It wants genotype frequencies. And then it says, assume we are in Hardy-Weinberg equilibrium. You're always going to see that caveat attached to every single problem. And as we'll soon discover, never are we in Hardy-Weinberg equilibrium. But let's set that aside for right now. Okay, so really important. You want to run with the recessives. So you've got to identify what is the recessive phenotype. In this case, it's white. And recognize that there is only one genotype that will give you a white cat, and that is little b, little b. I'm using B in this instance, but you can use A or whatever letter you prefer. I like A's and B's because it's easy to see the difference between the lowercase and the uppercase. But most importantly, homozygous recessive genotype is the only way that you're going to get the recessive phenotype. There's two ways to get black cats: homozygous dominant and heterozygous. We don't know, of these 84 black cats, what proportion are big B, and what proportion are big B, little b. But we do know the genotype frequency for the homozygous recessives. We're given that in the word problem. You're always given Q squared in the word problem. So there are 16 little b white cats. Remember, Q squared is the frequency of the homozygous recessives. So in order to find the frequency, which means it's going to be a decimal less than 1, I'm going to take the total number of individuals that express the recessive phenotype, and I'm going to divide by the total number in the population. 0.16 is Q squared. Okay. I would recommend on all of your problems rounding to 3 decimal places. In this case, I've just gone to 2 because the third decimal is a 0. So again, Q squared, you're going to be able to, you're either going to be given it directly or you're going to be able to calculate it from the word problem. Okay, so step 1, identify Q squared. Step number 2, solve for Q. So we need to know what is the frequency of the recessive allele of little b. In order to solve for the frequency of little b, which is just Q, all we're going to do is take the square root of Q squared. And so in order to go from Q squared to Q, all we have to do is take the square root of Q squared. The square root of 0.16 is 0.4. This is a little bit confusing, but remember, when you take a square root on a decimal, the number is actually going to be larger, okay? So what this is saying is 0.4, or 40% of the alleles in this gene pool are little b. Think about it. You have 100 cats. Each has 2 alleles. So there's 200 alleles total. So of those 200 alleles, 40% are little b. We're dealing with a 2 allele system. So the only other allele we could have is big B, the dominant allele. We know that Q equals 0.4. So now we just solve for P. Remember, P is the frequency of the dominant allele. 1 minus 0.4 gives us 0.6. Now we're in really good shape because now we have our allele frequencies. Q equals 0.4 and P equals 0.6. Remember, my question wants the frequency of each genotype. What proportion are homozygous dominant? What proportion are heterozygous? What proportion are homozygous recessives? So once I have my allele frequencies, it's pretty easy. I'm just going to plug and chug. Remember, I was given Q squared right out of the gates. We know that that's 0.16, 16 divided by 100, okay? To solve for the heterozygotes, I'm going to go back to those Hardy-Weinberg equilibrium equations, and I'm going to think about the genotype frequencies. So we know the frequency of the heterozygotes, big B, little b, is 2 times P times Q. Remember, I've solved for P and I've solved for Q. 2, okay, times P times Q. Remember, with multiplication, it doesn't matter the order that you put it into your calculator. 0.4 times 0.6 times 2 is the same as 2 times 0.6 times 0.4. Okay, and so when we multiply those 3 values, we get 0.48. So 48% of these cats are heterozygous. In order to solve for the homozygous dominance, again, we go back to those equilibrium equations. We know that the frequency for homozygous dominant is p squared. So you're going to do 0.6 times 0.6, which equals 0.36. And I have now solved for the frequency of each of my genotypes. How do I check my work? Remember, only 3 genotypes, so they should sum to 1, 0.16, 0.48, 0.36. If I get 1.00001 or 0.99999, I'm not worried about it because I know that's just rounding. To summarize, these are the steps that you're going to follow every time on every single word problem. When you read carefully the word problem, you're going to hear me saying, run with the recessives. Remember, you're going to either be directly or indirectly given Q squared. Q squared, of course, is the frequency of the homozygous recessives. There's only one way to get a recessive phenotype, to get a white cat or a wingless fruit fly, and that's little a, or little b, whatever letter you want to use. If you're not given Q squared directly, to solve it, all it is the number of individuals that express that recessive phenotype divided by the total population size. So you've got Q squared. You're given it in the problem. Step number 2. Once you have calculated Q squared, solve for Q by taking the square root of Q squared. Now you have the allele frequency for the recessive. Remember, there's just a recessive and a dominant. So next I'm going to solve for P. In order to solve for P, the allele frequency for the dominant allele, I'm going to do 1 minus Q. Then I have solved for both Q and P. So now, in order to get my, now that I have my allele frequencies, in order to get my genotype frequencies, I'm just going to plug and chug P and Q into the equation to get the heterozygotes. 2 times P times Q is the heterozygous frequency, and P squared is the frequency of the homozygous dominance. Some hints before you do some practice. Well, first hint is just practice. Roll through these problems, and just, if you don't get them the first time, remember you get 2 attempts on the quizzes, okay? First hint that I will give you is always, especially on the assessments, double check your work by ensuring that P plus Q equals 1, the allele frequencies, as well as your genotype frequencies. P squared plus 2PQ plus Q squared should sum to 1 or very close to it. Maybe it's 1.001 or 0.999. That's cool. Second hint, I would recommend rounding to 3 decimal places. No more, no less. I've been doing this a long time. 3 decimal places is going to give you enough precision so that you're not going to arrive at a weird answer. But with only 3 decimal places punching into your calculator, you're much less likely to make silly mistakes. So when students are punching in like 12 decimal places, that's when they tend to make a mistake. Hint number 3, use a calculator. Even when you're solving for P from Q and it's pretty simple mental math, just get into the habit of punching it into your calculator, at least on the assessment. I've seen too many students that do the mental math and they, make an error. And so that really stinks. And then lastly, after completing all those mathematical steps, those 4 steps, reread the question and determine what the question is asking for. Is it asking for an allele frequency, P or Q? Or is it asking for a genotype frequency, the frequency of the homozygous dominants, the frequency of the heterozygotes, or the frequency of the homozygous recessives? Okay, practice, practice, practice. And I've got some more resources in here that will help you. And if it's just not making sense after rolling through this learning activity and watching the extra resources, reach out to me and I'll set up a video conference with you and walk you through a few more problems before your assessment. Cool. Have fun.